Hello everyone, I'm Dianshu Liao, a third-year PhD student from the Australian National University. Today I'm very happy to present our paper titled junitgenie, a framework for path-sensitive unit test generation with large language models. So let's start from the background. Unit testing is essential in software development as it enables early bug detection, avoiding exponential costs in production. Additionally, it is fast, as developers can run it frequently whenever a change is made without slowing down the development process. Moreover, it serves as a form of documentation, as every unit test explains how a specific function is expected to behave. However, writing tests is complex and time-consuming. For many developers, it can take up a lot of development time, which increases their workload. To reduce this burden, researchers have explored automated unit test generation. In general, there are two main approaches: the traditional heuristic-based and the large language model-based approach. While heuristic-based approach can generate many tests automatically, they rely on predefined rules. This means they don't actually understand the logic of the program. As a result, they often fail to handle interdependent constraints within the program. For example, Evo3 tends to explore large irrelevant input spaces, wasting time during test evaluation. Rundoop, on the other hand, randomly combines methods without logical understanding. So this approach struggles to cover complex paths, especially those requiring precise conditions. Recently, researchers have leveraged large language models' semantic understanding to generate tests. For example, chat tester, cover-up, and hits. However, current LLM-based approaches are path insensitive, which hinders reasoning about control flow branches. In addition, they lack symbolic reasoning abilities, making it difficult to handle tests that require precise program behavior. Moreover, many approaches prompt LLMs with limited context, forcing the model to guess missing dependencies. Even when full context is provided, excessive irrelevant context dilutes the model's attention from the focal method. So overall, neither heuristic nor LLM-based approach can effectively generate path-sensitive tests. To address these challenges, our insight is to enable path-sensitive unit test generation by providing minimal yet sufficient contextual code knowledge for LLMs. Based on this idea, we developed junitgenie, a framework that guides LLMs to generate high-coverage and executable unit tests. junitgenie is built on three models: context knowledge extraction, context knowledge distillation, and test generation with feedback loop. Starting from a Java project, junitgenie extracts comprehensive code knowledge. This includes type information, control flow information, and data flow dependencies. All this information is stored in a code knowledge base, which we later use to retrieve relevant context. Second, for each focal method, junitgenie explores its control flow graph. Instead of analyzing the entire graph at once, it traverses each path individually. Then, for each safety path, it retrieves and deduces the only minimal required context, the focal method invocation strategy, the dependent variables, and dependent method constraints. Finally, the distilled context is composed into a structured prompt and fed to the LLM. Since the generated test may have compilation or runtime errors, junitgenie applies a feedback loop. It captures the error messages, refines the test, and repeats until we get a fully executable test. To construct our dataset, we select 10 real-world Java projects from Device4j and using their latest versions. Since trivial methods are easy to cover, we focus on more challenging ones. We select methods with branching logic or external dependencies, so they require reasoning about control flow and data flow. We then randomly sample to balance evaluation cost and diversity. In total, the dataset includes 2,258 methods from 762 classes across 10 projects. We first evaluate the effectiveness of junitgenie against both heuristic and LLM-based approaches. The results show that junitgenie achieves the highest coverage, and on average, it improves branch coverage by 29.6% and line coverage by 31%. We then evaluate the generalizability of junitgenie. We conduct experiments on 4 models, GPT-4o mini and 3 open-source models. For each model, we consider 2 settings. The first is basic prompting, which uses only the focal method source code, and the second applies the full junitgenie pipeline. As shown in the table, junitgenie consistently improves both branch and line coverage by 26% to 38% across all models. This is a demo to demonstrate how junitgenie analyzes a complex real-world focal method to generate tests for high coverage. The focal method condition C0 is from the Apache Commons Code C project. With different inputs, this method can take multiple execution paths. If contains method returns true, the focal method returns immediately. Otherwise, it proceeds to the next condition. Overall, there are 4 different branches. In addition, the execution of the focal method depends on external methods. For example, it relies on the return value of contains, isvolve, and char@. Moreover, these dependencies can be nested. For example, the focal method depends on isvolve method, and the method isvolve further depends on the method index of. In addition to method dependencies, the execution also depends on variable values. For example, the method isvolve depends on the variable volves, which influences its return value. To handle complex control flow, junitgenie adopts a path-by-path strategy, generating tests for one execution path at a time. For example, we consider a path where the first check fails, then the execution moves to the next condition, and the index condition is satisfied. Then the method returns false. Given this specific execution path, junitgenie distills the key information required to generate tests that cover this path. First, the focal method condition C0 is private and cannot be invoked directly, so junitgenie uses reflection as the invocation strategy. Next, junitgenie derives input constraints to ensure that the execution follows this specific path. To make this first condition fail, the method requires the initial check to return false. By analyzing this condition, junitgenie infers that the index must be less than 0, while the value remains unrestricted. Then, to ensure the next condition is satisfied, the index must be less than or equal to 1. Finally, junitgenie combines all constraints and derives the final input condition. The index must be less than 0, while the value is unrestricted. Finally, junitgenie generates tests based on the distilled context. It then verifies whether the generated tests are runnable. If not, it analyzes the error message and refines the test code accordingly. For example, if a required test annotation is missing, it adds the necessary import statements. The process continues until a runnable test is obtained. So this is a demo to illustrate how to utilize our junitgenie.
This is the GitHub repository for junitgenie. The README provides prerequisites, installation steps, and quick start instructions. Given a project containing the target focal method, we first compile it. Then, junitgenie extracts context code information through AST and bytecode-based analysis. This information includes method declarations, signatures, access modifiers, hierarchy relationships, and more. Next, junitgenie structures this extracted information into code entities and the relations between them. All structured data are saved as CSV files, including CFG path entities, class-level entities, and relations such as hasCFG path and hasMethod. junitgenie then uploads the structured contextual information to a Neo4j database for subsequent retrieval. This is a simple example of a method code entity and its relations, such as has CFG path, its class-to-method relation, and its parameter relation. Through these relations, we can retrieve other context, such as the methods and variables defined in the same class. Based on this database, we can specify a method for junitgenie to generate tests that cover all its possible execution paths. To do this, we provide the focal methods fully qualified name, project directory, and package name. In this example, junitgenie identifies 9 execution paths and generates tests for each. During generation, junitgenie distills path-specific context, feeds it to the LLM to generate tests, and iteratively refines the results based on detected errors. junitgenie saves one test file per CFG path in the test directory. Now, let's run the generated tests. We can see the tests cover all branches and lines of the focal method. Overall, junitgenie enables automated, path-sensitive test generation with high coverage. Thank you for watching.
So finally, this is our takeaway. First, junitgenie enables path-sensitive unit test generation by distilling minimal yet sufficient contextual knowledge. It focuses on one execution path at a time, it derives precise input constraints, and it generates runtime test, runnable test with feedback refinement. The second is junitgenie achieves effective coverage for complex code, and our code is available at our GitHub repository. Thanks very much for your attention.